our transformations unit. And how do we use our transformations unit to graph new things like this? So first of all, you would have to recognize, so I'm going to graph that one in green. I'd have to recognize in that graph that the base is 2 and the exponent is x. So off to the side, I draw a quick graph of 2 to the x. I know that 2 to the x has an asymptote here, and the important points are 0, 1, and 1, 2. That is our exponential graph. Now, to graph the green equation using transformations, first, I'm going to write out this in factored form. Remember, when you have a horizontal stretch, reflection, or compression with a horizontal translation, we had to write it in factored form. Now, another thing I like to do in these questions is I like to put, in this case I'm putting a box around the 2 to the x to remind myself that is part of my parent function. The 2 is not a transformation. I can label the other transformations. The 3 is going to be a vertical stretch. You're going to multiply your y values by 3. The negative is going to be a horizontal reflection. You're going to multiply your x values by -1. And the -2 is a horizontal translation. You're going to go to the right. And the reason we didn't do these in our transformations unit, it was a +2, and I factored out the negative. So you're going to be tempted to go 2 to the left, because it wasn't in factored form. So the reason I put the box around the 2 to the x, well, actually 2 reasons. One, sometimes people get confused and call that a horizontal or a vertical shift as well. You have to remember that 2 is part of the original function, so it doesn't affect any transformations. Also, we have to be careful here. Order of operations, you will be so tempted. You see 3 times 2, and your brain is so happy. It's like, I know my times table. I'm so good at my times table. You will be tempted to write 6. When you see 3 times 2 so close together, can you see yourself getting tempted to write 6? But we have to remember our order of operations. We do exponents before we multiply. So before you could multiply 3 times 2 and get 6, you have to do all that exponent first. And there's a variable there, so you cannot do 3 times 2 and write 6 because of order of operations. Now we are going to do the points and the system for this the same way we did in transformations. So you're going to have to read a little bit of a review. Do you remember when we took the points? We had 0, 1, and 1, 2 on our original graph. And then we would do our stretches, compressions first, and then translation second. Above here, I can say I know that I need to multiply my y value by 3, my x value by -1. And I know that I need to go 2 to the right. So what's going to happen to 0, 1? Well, x by -1 won't make a difference, but it will go to 0, 3. And then I'm going to move 2 to the right. So I'll have the point 2, 3. 1, 2. X by -1 will be -1, 6. 2 to the right, 1, 6. And we also have to figure out what's going to happen to our asymptote. Our asymptote is at y equals 0, horizontal. Multiplying it will never make a difference because it's at 0. The only thing that's going to make a difference on a horizontal asymptote is if you're moving it up or down. And we're moving this one to the right, so horizontal line moved to the right is still going to be exactly in the same place. So this asymptote is going to stay at y equals 0. And at this point, we can draw our graph. So, I can draw my asymptote at y equals 0. I can label my 2 points. One point is at 1, 6. The other one at 2, 3. And we can draw the shape of our exponential graph as a result. Oh, it just hit the 40th minute of the soccer game. Okay, I'm going to do another example with you. Another couple of examples. So I think you still have some space on page 346 at the bottom. Has everybody done this? Need me to scroll up? Okay, so let's just practice some more of these graphing. This is basically what this first lesson is relearning our transformations unit. We're going to graph y equals negative 5 times 3 to the, this one's already in factored form. Y equals negative 5, 3 to 2x plus 4. So, first of all, we would have to recognize this as a 3 to the x graph with transformations. So off to the side, I draw a quick sketch of 3 to the x. So I quickly label everything that's happening here. We have a vertical reflection and a vertical stretch. You're going to be multiplying your y values by negative 5. You've got a 2. X values are going to get multiplied by half, horizontal compression. Moving 4 to the left and 1 down. And so we can take our original points, do the stretches and compressions first. So above here, I'm going to say, I know I'm going to multiply my y by negative 5, my x by a half. Then I'm going to go 4 to the left and 1 down. What happens? This will be 0, negative 5, and 1 half, negative 15. 4 to the left, negative 4, negative 3.5, 1 down, negative 6, negative 16. Also looking at our asymptote. Can you see this time we are moving 1 down, and so our asymptote will get moved 1 down as well. So when I go to graph this, asymptote at -1. I have a point at -4, -6. And at -3.5, -16. Join those points, make it go towards the asymptote, have the same kind of curve as an exponential graph, and you would be done graphing. So we could have introduced this as a parent graph in our transformations unit, but doing it this way gives us a good opportunity to review all of our transformations unit, which is going to be good for your exam, and introduce the exponential graph at a later time. Okay, we have 2 more graphs we're going to do. And today's exciting, so I think you have room on page 357. Page 357 is, and I introduce you to a new number. And you might say, that's a letter, Mr. Jr. No, the number E. It's on your calculator. See if you can find it and see what it's equal to. Sometimes they use E for times 10 to something, but this is a little e. That's usually a big E. It's 1. It's not equal to 1. Good. See if you can find what the number E is equal to. Not an error. Find the E button on your calculator. Yes. There it is. Hey. E is approximately 2.718281828. What do you think the next 4 numbers are? It looks like it should be 1828 again, right? But it's not. It is a crazy number like pi. This kind of pi. You know how pi is 3.1415? Da 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 da. Okay? And pi is more famous than E. But E and pi belong to a group of numbers that are special. They're more special, like, for one, they're irrational, okay, which means that there's no pattern. After that, it sure looks like this one has a pattern, but it doesn't. There's no pattern, they're irrational, but square root of 2 is irrational, and they call E and pi a group of numbers called transcendental numbers. Square root of 2 is an irrational number. It's called an algebraic number because you can make a polynomial and solve and get the square root of 2. But with E and pi, you can never make a polynomial equation with that as an answer. And so they have this special name for those numbers. And actually, this is some crazy math. Okay? They have proven that there are tons and tons and tons of transcendental numbers. But they've found it very, very hard to find them. We know pi, we know E, we know combinations of them, like e to the pi and pi to the e and stuff like that. But we haven't found that many of them. But they can prove that there are, this is some abstract math for you today, okay? When you're working with infinity, things get a little bit complicated. Would you say there's an infinite amount of whole numbers? Yes. Okay? And there's an infinite amount of transcendental numbers. But they have proven that there's infinitely more transcendental numbers than whole numbers, even though there's infinity of both. Just kind of like blow your mind. They've proven that there are more irrational numbers than rational numbers, even though there's an infinite amount of both. And one way to sort of see this is if you took a meter stick, on a meter stick from 0 to 100 centimeters, there's every number included, right? If you randomly took a sword and cut the meter stick in half, every single time you'd end up on an irrational number. Basically. Even though there's an infinite amount of rational numbers and an infinite amount of irrational numbers, there's more of one than another, which is weird math. We won't get into that craziness right now. But for right now, we've introduced a new number. It's the number e. And if you had to graph e to the x, it's relatively easy. Every exponential graph has what point? 0, 1. This one's going to have the point 1, e. And it's going to have the same shape as all of our other exponential graphs with an asymptote at y equals 0. And if you know the graph of y equals e to the x, we can now do our transformations and graph things like this. Y equals 3e to the x minus 2 plus 1. So again, you would recognize the e to the x as your parent graph. The 3 is outside your function. That's going to be a vertical stretch. Multiply your y value by 3. The minus 2 is going to be a horizontal translation, 2 to the right. And the plus 1, a vertical translation, 1 up. So just like all of our other examples, you could take your original points, which were 0, 1, and 1, e. Do our stretches and compressions first. So what happens to 0, 1? It becomes 0, 3. What happens to 1, e? When you multiply by 3? It becomes 3e. Just sounds like you're saying 3 more excited than normal. So we got 1, 3. And if you move 2 to the right and 1 up, you're going to be at 2, 4. And here, you're going to be at 3, 3 plus 1. Now, graphing this. Oh, we should also look at what's going to happen to our asymptote, which is at y equals 0. You're moving 1 up. It's going to be at y equals 1. We'll draw our asymptote in at y equals 1. 2, 4 is easy to plot. 3, 3 plus 1. Well, if you think of 3 as 2.7-ish, if you multiply that by 3, you get 8.1. You could estimate this to be around 8.1 plus 1, 9.1. So I'd go to 3 and 9.1, and I just estimate about where that would be is enough to get the shape of the graph to look like this. Now, it's not hard with a new number, but it's just weird because you've never seen the number e before. And the number e becomes important in calculus because this graph is the only graph in calculus where the derivative is itself. You don't know what a derivative is. You don't know what a derivative is yet, but E is important because the derivative of e to the x is e to the x, and it's the only function whose derivative is the same as the original function. So you'll learn that hopefully next year if you take calculus next year.